also like to welcome all of you to this workshop in name of Gordon, Manfred, and Lorenzo, who unfortunately cannot be here. We are very happy that you could all come, and we hope that you will enjoy the workshop. There are two announcements. First of all, there is a schedule change. So on Tuesday, 11:30, we have Slava Richko, and on Friday, 2:30, we have John Imri. And then the second announcement concerns the lunch today. It will be a little bit shorter because actually the Churchill's College starts serving at 12:15. So you don't have to hurry up there. You have time to find it, but then maybe a little bit of rush to come back here. Okay, and we have our first speaker, who is Giovanni Jona-Lasinio, and he promised to give us some homeworks for the week. Namely, he will present some open questions and remarks on the theory of singular stochastic PDEs.
Thank you very much, Martina. Okay, thank you. Well, good morning to everybody. Of course, I am thankful to the organizer for inviting me. Well, I had the chance to participate in the early stage of formulating the program for this semester. And then also there are some historical reasons, because with my friend and colleague Prof. Mitter, over 30 years ago we studied a first example of singular stochastic PDE, and we showed that one could give, using methods coming from physics, in particular from constructive field theory, one could give a mathematical meaning to such equations. And then at that time we didn't suspect that this would develop in such a big subject as it is today. So what I will discuss are some simple points that, well, the abstract you know already. And then finally, well, as Martina said, I will give some homework for everybody. So let me first just a short introduction with some, more relaxed information. So the first topic is that there are singular stochastic equations which are quite extensively used by physicists, and they are quite effective, but they have no mathematical meaning. So, but as a kind of introduction, let's remember what are the equations which have been studied so far. Well, first one, an important one was the KPZ equation, Kardar-Parisian-Zhang equation, and you see the problem with an equation of this kind, if you make this substitution here, you get an equation which is nonlinear, and this is stochastic Boltz's equation, and which has the form of a conservation law, and you see is nonlinear since the solution. This is white noise in time and space, and so the solutions, if they exist, are distributions. So the square of a distribution doesn't have usually meaning. You can also make another substitution here, and then you get a stochastic heat equation, but you get a multiplicative noise, which is something more complicated to deal with. Another kind of equation was those that came from stochastic quantization. This was an idea of due to Parisian Wu, and who proposed it heuristically for some problems of gauge fixing in gauge theories, and but they didn't do any mathematical effort to give a real meaning to these equations, which were used in at the perturbation theory level. But then with Pronob-Bitter, we tried to take seriously such an equation, and you see, the idea of stochastic quantization is that one way of studying the measure for Euclidean field theory is to think of it as the equilibrium state of some Markov process. And so, you see, this is a stochastic nonlinear equation, and this equilibrium measure, the formal equilibrium measure for this equation is just the one studied by Euclidean field theory, which at that time had been, it was a theory which was quite advanced. So this is a Gaussian measure, and of course this, you see, the potential is a fourth order monomial, and since again the typical sample of these processes are distributions. So I mean, for this measure, techniques have been developed by constructive field theory, but our idea was to try to give a meaning, a mathematical meaning also to this equation. And so this equation cannot be taken literally. They involve powers of distribution, and they have to be modified to become mathematically meaningful. This is the renormalization problem. And there is not a unique way to renormalize. One follows the explained gained with quantum field theory. In two space dimensions, there is it's enough to replace the powers of the field with the so-called weak products according to the rule, and H is an arbit polynomial. The only about the renormalization process, the only thing that physics requires is that experimentally measurable quantities do not depend on the way you renormalize, because otherwise there would be too much arbitrariness. So, but of course, from the mathematical point of view, you can follow different patterns from those typically followed by physicists, and this is what has happened more recently with the Haber theory. And so, in the case of but that we treated with Mitter, we treated a slightly modified equation, because you see, in order that because we could not treat exactly the equation as that I mentioned before. This is obtained only for this parameter rho equal to 1, and but you see, we did things in such a way, so we regularized a little bit the noise, but on the other hand, we changed the drift of this equation in such a way that the measure, the invariant measure, remains the same. So the drift is more singular, But that we could deal with this problem, while the noise is slightly regularized. And you can also write a mild version for this equation, and this is the solution for the linear, for the Gaussian field, which is a Gaussian process. Okay. And so what we defined were weak solutions in a probabilistic sense. What does it mean? It means that the evolution is defined by an expression of this kind, and this quantity z is what is called the Girsanov exponent, which allows you to, but you see, for this to work, I mean, you must have some absolute continuity of the evolution measure with respect to the Gaussian process. And this is why we had to modify the equation, but still keeping the same invariant measure. And this is the structure of the Girsanov measure. Phi naught is just the initial condition, and this is any function of, I mean, in a certain class of phi. Okay. On the other hand, later, about, well, this work was done, our work was around 84, 85, so it's over 30 years ago. But then at the beginning of the year 2000, there was a paper by Da Prato and de Bush, which was a real turning point in this game, because they showed that you could have strong solutions. Strong solutions means that for every trajectory of the noise, you can associate a solution of the stochastic equation. Okay, this the trick was the following. They represent the solution of the equation as the sum of two terms, in which they isolate the Gaussian process, which is represent the most singular part of the of the solution. This is the so this is the Gaussian process, and then if you rewrite the equation, the field, the solution in terms of this field y, you see that you get an expression which is smooth in this y, while you have no continuity properties with respect to the weak product to this. So the equation becomes more tractable, and then you can, at this point, they actually were able to identify some Bezoff spaces in which the solution is strong. And now let's come to the, so that was, now there has been an enormous development connected also with the higher theory of regularity structures, but also with methods more standard than the theory of PDEs, especially in the work of Murat and Weber. And so there are now many ways to treat these strong solutions, and so the theory developed a lot. And then there was the approach by rough path and paracontrolled path by Gubinelli and Perkowski and others. So now it's the thing developed in a really big theory and very technical. I mean, now, however, there are equations which are widely used in statistical mechanics, especially in the theory in non-equilibrium, there has been an important progress in understanding diffusion processes out of equilibrium in the last 20 years. And but you work with equations which so far have no mathematical meaning, and I will explain why. On these non-equilibrium problems, I've been collaborating for many years, and even now with Lorenzo Bertini and others. And I think it was Lorenzo Bertini who pointed out first that these equations have no meaning, are beyond the present theory. So, what is fluctuating hydrodynamics? That is an idea that goes back to Landau long ago, but he used this idea only in linear cases. So there was not too serious mathematical problems. But now the equations that are being used now are always nonlinear, even in the simplest models. And all the interesting physical effects depend on the nonlinearity. So, these hydrodynamic equations, and you have to make certain assumptions, but for many models, especially of gas lattices, they can be proved rigorously. And sorry. So you have usually conservation laws. For example, matter is conserved in a process, and so you have certain conservation laws, and then which are associated with what are called traditionally constitutive equations, which in this hypothesis of local equilibrium, this means that this current can be expressed actually in terms of gradient. I mean, in order to, especially non-equilibrium, in order that a current goes through the system, you must have some gradients or external fields. And what is let's say this introduces two what are called by physicists transport coefficients. This is the diffusion coefficient, which multiplies the gradient of the density, and then you have the mobility or conductivity, which are usually have a dependence on the density. This density can be a vector, you have usually several conservation laws. Besides matter, you have momentum and other things. Not energy for diffusive processes. Now, what characterizes non-equilibrium or also fluctuations is the fact that a current is flowing through the system. So you have a new thermodynamic variable, which actually in its definition contains time, and this makes a lot of difference. And you have to do some what I call space-time thermodynamics. Now, about how these equations arise, well, next week I will give a seminar on non-equilibrium, but so those of you who will be here maybe might be interested. So okay. Now, apply the idea of Landau. The idea of Landau is that you have to add to the current a white noise in space and time, but with a coefficient which contains the conductivity, and which is, even in the simplest models, is a nonlinear function of the thermodynamic variable, and all, as I said, interesting physical effects depend on this nonlinearity. So, so if you insert why, well, I will explain that in a seminar, but why you want to add to the current? Take this is if you want, is a physical principle, but the idea which is behind is that the stochastic perturbation comes from a fluctuating force, so from a fluctuating external field. So the environment in which hydrodynamics, I mean the system lives, is immersed in some kind of stochastic force. Now, if you insert this term here in the continuity equation, you see you get this kind of stochastic equation. Now this is very bad because you see here you have the gradient, so you will get two additional terms. I mean, from the derivative of this term you get a multiplicative noise of the white noise, and then you have an extra derivative of the space derivative of the white noise. And these are, I asked also higher. I mean, this is definitely beyond what can be done with the present theory. So, but now you see, these equations actually are very useful because they have been applied in a very large number of cases, and you get exact results. Exact, I mean that they coincide with what you get for microscopic models which can be solved exactly. So, I mean, this equation must have some mathematical content. You see, take for example the simple exclusion process. Already in this case is this chi, this mobility is a quadratic function. So already in this simple one-dimensional case, this equation has no meaning, as far as we know so far. However, for example, you can from this equation formally, you get a large deviation formula for the current and the density, a joint, which is very simple. You see, it's a quadratic expression, which for a physicist is very pleasant, because think of an electric conductor, and so this chi minus 1 is the resistance. So this is just the dissipation of this extra current with respect. This is the hydrodynamic current, and this is the fluctuation. So it's just the energy dissipated by the power dissipated by the okay, and for example, from this formula, everything in this theory of diffusion, non-equilibrium diffusion processes follows from this unique formula. And for example, you can express the large deviation functional for the invariant measure, and in terms of this variational principle, where this is just our exponent. And in fact, you can prove rigorously. I think the last step was taken by Thierry Baudineau, I think, in proving that this is the correct definition of the large deviation functional for so and this is the And what you get, you see, in the large deviation theory, using this equation formally, you get exactly what you would get if the Friedrich-Wenzel theory for dynamical system were applicable in this case. And but I will come back to that. For example, for the simple exclusion, you can calculate this, you can solve this variational principle, and you see, this is the part which comes from non-equilibrium, which is quite non-trivial because you have to solve such an equation, which is a highly nonlinear equation, ordinary differential equation, and this expression was first calculated by Derrida, Leibowitz, and Sperr by solving the microscopic model. So it was a direct calculation, a microscopic calculation which required about 40 pages of calculations. But then we calculate the same thing from this formal equation, and by solving the variational principle, and we got the same expression in 3 lines. So this showed us that we were on the right track. And so somehow you have to explain why such an equation and you see the consequences of these stochastic equations have been tested in really a very, very large number of cases, and always it gives the exact result when you can calculate the same thing from microscopic principles. So they are very useful equations, and they are also somehow experimentally testable because the coefficients, I mean the diffusion coefficient and the conductivity, are measurable quantities. So you see, for the KPZA equation there was a very well-known paper by Bertini and Jacobin, and this was I think one should make a similar effort, both from the standpoint of microscopic models and from the standpoint of the mathematics, to give a meaning to such fluctuating hydrodynamics. And I mean, large deviations for this nonlinear equation, for the stochastic quantization equation, were studied by Mitter and myself already a long time ago, almost 30 years ago, and we had a paper in Communication in 1990, and more recently in 2014 Heirer and Weber approved large deviations for the strong solutions, and but there is an important conclusion on which we both agree, that is that the large deviation functional for these equations do not depend on the way you renormalize. Okay, another equation which has been used by physicists is this. This is a linear equation, but you see, with very strong singularities for the noise. You have these are Laplacians in different subspaces. So if you have you consider this equation in a d-dimensional space, you allow some anisotropy, and so and this equation has been proposed to model non-equilibrium long-range correlation of thermodynamic variables. And this long-range correlation, which is a feature of non-equilibrium situation, have been measured experimentally. So there are things which are on a very solid ground from the physical point of view. And it seems to me also mathematically, it's true that now, you see, these large deviation functionals have the meaning of thermodynamic functionals, like entropy. Actually, they are analogs of free energy. And so their singularity can give rise to new type of phase transitions and so on. And well, okay. Of course, it is true that very different equations may have the same large deviation functional. So one has to understand, so far there is not a physical model for this white noise in space and time. So one should work on both sides. One to see whether one could give a meaning to the equation, and the other to provide a model, a particle model for this, for the fluctuating part. And this is, they are both very hard problems, but I think it's they are important. Okay, so this is a class of equations which I wanted to bring to your attention, which are physically relevant. Now, the second point I wanted to say something about is the fact that actually these equations are stochastic dynamical systems. They are PDEs and stochastic PDEs, and so you might one should also look at these equations from this point of view, and this raises several questions. For the interesting dynamical systems are systems in which you have a non-gradient part. If you want to have non-trivial attractors, you must have now in 91 with Roland Seneor, we studied a special case of this equation. So we studied this particular equation, and you see there is a non-diagonal part, so this is a non-gradient system, and it has an attractor which is correspond to this. This is this field has two components, and you have when the square modulus is equal to 1, you get an attractor. Now we apply this to the weak solutions, because at that time we didn't know yet about the existence of strong solutions. But so we renormalized with weak products, and you have to define these weak products of and then you put back in the equation, and the equation is meaningful. Now, the conditions under which we were able to prove existence of the weak solutions in this case, we had the condition for which the gradient part dominates over the non-gradient part. And this was connected with giving meaning to the Giesanov exponent and so on. With the and you see this dominance condition is expressed by this relationship, in which this negative part, which is associated to the diagonal part, dominates. And so we had a constraint. Now, my question is, I mean, one should try to extend these things to equations having strong solution, and especially equations which have non-trivial attractors, like chaotic attractors or so on. And for example, this equation might be very relevant in the theory of turbulence. I mean, so. Now, when you, in general, when you speak about fluctuations in this in equations whose solutions are distributions, you have to consider that it's, you see, what is a physical quantity that you may want to study? Is the average of this field, of this hydrodynamical field, over a region. Now, this region can be small or can be large. Now, since there are ultraviolet divergences, fluctuations are much stronger when you average over a small region. So, the fact that you are in an asymptotic regime of large deviation depends very much on the scale on which you study your physical variable, because otherwise, I mean, you have the fact that the intensity of the noise depends on the scale over which you study your field. And now, so this is something to consider, and since in any concrete problem you have to decide what is the error that you want to allow and how much you are in the asymptotic regime of large deviations. And so you would like to know how the maximal intensity that you can allow for your noise and the error allowed scale with the size of this region. This is very important information. Let me be, well, in this large deviation studies that I mentioned before, in the one with meter we took into account the scale over which, while I mean Heirer and Weber proved just the fact that you have a large deviation principle. So now let me be more concrete, because to see what I mean when I say that what I want to be, I would like to know how they scale with the size of the region. Let me recall the Wenzel and Friedling theory for dynamical systems, because actually these are the estimates you would apply in a concrete problem. Now you have so this equation is a finite dimensional equation, so there are no problems of distributions. You have an action functional, which is this one, which is well known, and then you make estimates, which let me essentially tell you that the probability that your trajectory be close to a pre-assigned trajectory is essentially of the order of this exponential, provided well, gamma is an error term, and epsilon must be below a certain epsilon 0, which is which defines when you are in the asymptotic regime. Now, exactly what one would like to know, how they depend, in the case of distributions, how the quantities like gamma or epsilon 0 depend on the scale over which you want to study your field. Because I mean, you have to decide what, how much error you can allow, and then you want to know whether you are or not in the asymptotic regime. Okay, so okay, this is there is a reformulation due to Varadan of this Wenzel and Friedlin estimates, which is given here. But the Friedlin-Wenzel estimates are more explicit. Okay, another concept that you have, which I think is important in dynamical system, even in stochastic dynamical system, is the concept of Lyapunov function. Now, there is a notion of Lyapunov function for finite dimensional system. So this is the generator of the diffusion process. Actually, it applies to more general processes, like now there are very fashionable Levy processes, and this can be the generator of any process. But let's stick to diffusion processes, and then this V is a stochastic Lyapunov function if this inequality holds, where C1 and C2 are positive constants. However, is there an equivalent for the case of singular stochastic equation? You see, take a stochastic quantization equation, but we regularize noise. So it has trivially strong solutions. And then, I mean, a simple stochastic Lyapunov function is given by L2 norm of your field. But this expression in the case of distribution has no meaning. And then it's I haven't tried very hard, but it's not immediate to find what could be a substitute of this for the case of distribution. Now I want to just give you an example of what I was saying before, that the fluctuations are very different according to the scale. This is again a work done almost 30 years ago, and with two people working in atmospheric physics. Actually, we wanted to apply this nonlinear stochastic equation to some atmospheric physics problem, but I think the application now is obsolete. I haven't followed what happened in, but we wanted to verify, because that was the physical phenomenon that at that time was believed to be the case. I don't know now. That fluctuations on different scales maybe they're very different. You know, we studied this equation in 2 dimensions and introducing the renormalization term. So the idea was that even the renormalized equation, so the modified equation, could have a physical meaning, which in this case could be interesting. Then you see, so we have a lattice, and we discretize the equation, and you have an effective mass term, which is given by this expression. Okay. Now, for sufficiently large coupling constant, and for appropriate choice of the parameters, the weak product induces a double well potential. This is what at the origin of phase transition in the 5^2 theory in the infinite volume limit, and it was proved long ago by Glim, Jaffe, and Spencer back in the middle 70s. And now, however, if you are in a finite volume, you don't have 2 separated phases. You have a double well, but the process could tunnel from one well to the other, and so you would expect that your distribution, stationary probability distribution, be at 2 peaks corresponding to each of the wells. Now, then we did simulations. Of course, the techniques for simulation at that time were very rough compared to now. And so we introduced a quantity which is the average of the field over a square, which could be smaller or larger. And then we studied the stationary distribution. Now, if you are not in this region of phase transition, you get a single peak. Okay. But then, if you study if you are in the region of the phase transition and you average your field over a large square, actually over the entire square, you get in fact a double bimodal distribution. And then you see that varying the scale, so averaging over a small square or large square, you get different results. You see, here in one point you get one peak, and then if you average over larger and larger square, there is the appearance of a second peak, and then for very large square you get a bimodality. So because the double well in small scale is masked by the fluctuations which are very strong and reappear only when your field has less fluctuation. Now, as far as I know, nobody has repeated this simulation, so I mean, my two colleagues were very expert, so I think the result is correct. But also, to such a phenomenon, one should give a more mathematical foundation, because all this was rather empirical. Okay. So the interesting feature is the absence of bimodal distribution on small scale. You see the advantage to apply it to a physical problem, since there were, in fact, in the statistics of jet streams, I mean, these high velocity currents in the atmosphere, there were two regimes, and we tried to explain them in terms of a unique equation, because the bimodality appeared only for low Fourier Fourier modes, while the unimodality appeared for large Fourier modes. Okay, so now just a few minutes, one thing that we did with Seneor, I mean, the Gliff, Jaffe and Spencer have developed a cluster expansion to study the infinite volume limit, and then Seneor had developed further to adapt it to the three-dimensional case. And so we thought that it could be a good idea to apply this thing in time, and this in fact was proposed again by Mitter more recently, and I believe at that time also Brickmont and Kupiainen had proposed some similar ideas in the study of infinite dimensional system. Do I remember correctly? You don't know. You wrote some rather formidable papers with Jean Brickmont for infinite dimensional dynamical systems.
That's right, but I mean, it's simpler than what you are telling about now.
Okay. Now, So we took a finite dimensional equation, actually a one-dimensional equation, which is gradient, so you know everything about the invariant measure. And suppose we want to calculate, we are some kind of masochistic attitude, you want to calculate by some very technical methods. And so we decided to apply the same methods they had applied in this infinite volume problem to the case of to study the infinite time problem. And so we started using again the Kirsanov formula, which in this case is perfectly and we were able to essentially to prove two statements that for lambda small enough. So this expression can be expressed as a convergent series uniform in T, and this series is provided by the cluster expansion. And then there exists a stationary measure such that now we wanted to then to apply it to at least to the weak solutions of you see this is very long ago to the case of field theory, but at that time Roland Senior was heavily engaged in the administration of the École Polytechnique, so we didn't do that, and this was too bad because Roland passed away a few years ago, and that was a big loss. So the expansion is defined by introducing an interpolation of the covariance of the Gaussian field. So you see for s equal to 1, this part disappears and you get the full covariance, and for s equals 0, essentially the covariance splits in two independent parts. So your measure also splits into two independent measures. And then you have to introduce some interpolating finite condition, and then you do what you do typically in this cluster expansion. You start from the s equals 0 situation, and then so the final interval of time is independent, totally independent from what comes previously, and then you have these second terms, and then you go on in a rather complicated way. The only pleasant thing in this approach is the fact that you exploit systematically the fact that your Gaussian process decays in time. So so this is a possible way to study the existence of invariant measures, also in the case of these singular stochastic equations. Okay, so I mean, I don't say anything more on this. So this is the homework. Provide a foundation, microscopic and microscopic, to fluctuating hydrodynamics. This, of course, is a very hard problem, but I think something must be done. Otherwise, our theoretical foundation is shaky. So then let's try the theory of strong solution to non-gradient equation, where the deterministic part has non-trivial attractors. And 2 years ago, I asked the question to Franco Flandoli. I don't know whether he's here. No, he's not arrived yet. Who is an inventor of these stochastic attractors? And he said, oh yes, it's very interesting. But then I asked again recently, and he said, no, it's not so interesting. I don't know. So apparently he has repudiated his child. But I don't know, maybe if he comes, I can discuss with him. And then, I mean, I would like to see the construction of stochastic Lyapunov functions for these singular equations. Well, I think this is a good point to stop, and thank you very much.
Thank you very much for a nice talk. Questions?
Yeah, one thing I always have difficulties understanding. That is why you want to have very singular noise. We don't really know the microscopic physics so well. So why couldn't one simply choose somewhat more regular noise?
I mean, this is part of the question, of the problem. I mean, because we don't have a model for this white noise. It's just a method that works.
Yes.
So, if you start from these equations, from this fluctuating hydrodynamics, and you apply it, you get good results always. But in fact, it's a physical principle. You don't know why it works. In fact, I think you have to work on both sides, the physical one and the mathematical one.
Yes, but suppose I just smeared out my noise a little bit. What would be wrong with the physics?
Well, I think then, because there are certain scalings which you have to respect. And if you don't use this white noise, you don't get the right scalings.
So when you discuss the notion of a non-trivial attractor, are you thinking of things like sigma models where you have a manifold of? Can you hear okay? When you talk about non-trivial attractors, are you thinking about manifolds like sigma models, or more like in finite dimensional dynamical systems you have orbits or strange attractors, things
well,
like
I mean, first of all, it would be interesting to study the case of simple attractors, because I mean, in the examples that I gave, I got this condition of dominance of the gradient part over the non-gradient part. I don't know whether this is necessary with the methods that exist now. So, I mean, then you have to define what does it mean for a distribution to be close to an attractor. I would imagine that for turbulence this might be interesting.
So for this hydrodynamic equations, you mentioned that the problem is hard because the conductivity is non-linear. But even if it would be linear, it would still be multiplicative noise. So is there some result in the linear case?
Well, that I don't know. You have to ask the experts.